Exhaust leaves the 4-foot diameter chimney as shown. Because of the wind, after a few diameters downstream, the exhaust flows in a horizontal direction with the speed of the wind, which is 15 feet per second. Determine the horizontal component of force of the blowing wind that puts on the exhaust gases. Density of the air is 0.00238 slugs per cubic feet. I love this problem, and it's nowhere near as complex as it looks. So let's just work through our steps just like we do with any other problem. First thing I want to do is I want to draw my control volume. And I want to have it split here at the pipe because I know what's going on there. I want to split it here where the wind is blowing the horizontal velocity. And then I'm going to complete my control volume. And from there, we can start applying our equations and what we're doing. And so what do we know about the problem? You know, from my thing, I know that the diameter at point 1 is 4 feet. I know that my velocity at 1 is 6 feet per second. My velocity of the smoke at 2 is going to be 15 feet per second. And then I know the density of my air is 0.0238 slugs per cubic foot. So looking at all that, we're going to make our assumptions. We can use our equations. We'll just put them right there. So what are we going to assume? Well, I'm going to assume a fixed CV. Why? Because that's the way I drew it. I'm going to assume one-dimensional inlets and outlets. I can make that assumption because, well, that's the way I drew it. Everything is orthogonal to the smoke. I ran out of room here, so we'll put 3 over here. What is that? That's steady flow. Why is it steady? There's nothing in it that says it's time dependent. And the last thing that we can look at is we're only moving at 15 feet per second, so it's well below a Mach number of 0.3. So we can assume that we have an incompressible fluid. We have a constant density. So from here, what we can do, same thing that we've done to everything else. We're going to apply conservation of mass, conservation of linear momentum. So let's do our conservation of mass first. So what does conservation of mass tell us? Well, that tells us that the mass flow rate in has to equal the mass flow rate out. And we know that mass flow rate is rho VA. So we can sit here and we can calculate everything that we need to know right off the bat. So m dot, we'll figure out the mass flow rate is rho 1 V1 A1. Now this one we could do rho 2 V2 A2. We know rho, we know A2, but we know V2, and we can just go and calculate that out. Actually, looking at this, no, we can't because we do not know what A2 is, but we could calculate out A2 once we do the mass flow rate. We're not really going to need A2 for this problem, so I'm not really going to worry about it. So let's plug the numbers in. 0.0238 slugs per cubic foot. There's my density. My velocity at point 1 is coming in 6 feet per second. My area at point 1, pi over 4, and it's 4 feet diameter, so 4 feet squared. So as I look at my units, I've got slugs, foot cubed, foot per second, foot squared. So slugs, foot per second squared. Actually, no, wait a second. Because we're mass flow rate, we want the slugs there. We don't want to convert that over to to force units. So we look at it. I have cubic foot down here. I have foot squared here, and I have a foot there, so the feet will all cancel out. And that gives me slugs per second, which would be a unit of mass flow, which is what we're looking for. So 0.179 slugs per second. And so that gives us our mass flow rate. The next thing that we need to do is calculate out what that reaction force is that's pushing on things. And so that reaction force is, we'll call that the reaction of the wind. That's what's pushing everything. We really have no gravity forces. We have no other body forces, so gravity, nuclear, electromagnetic fall out. We have surface forces. We have the pressures, which are all going to cancel out because it's just air that's already in air, so we're not worrying about that because I have the same air pressure pushing here as I have pushing here, same air pressure pushing here as I have pushing here. So those are all going to cancel themselves out. The only thing I have pushing on this is Rx, which is that reaction force from the wind. So now that we know the mass flow rate, let's actually look at calculating out that conservation of linear momentum equation.